Hi, good day, Professor. Today, me and my groupmates will be discussing our investigation into total hip replacement, or THR. But first, let me introduce me and my groupmates to you. I'm Kaiwan, we have Fatin, Yingqi, Shana, and Ahmed. Total hip replacement is a vital procedure for patients with severe hip damage. It has become a common solution for millions of individuals suffering from conditions such as osteoarthritis, rheumatoid arthritis, or hip fractures. Total hip replacement significantly improves mobility and quality of life, but challenges remain. These include mechanical failures, material degradation, and patient-related factors leading to premature wear or failure. To tackle these issues, our study focuses on optimizing design and material properties using statics and mechanics. We aim to pinpoint implant weaknesses, understand load distribution, and identify materials that can withstand the rigorous demands of hip joint movements. Our hypothesis is that by addressing static and dynamic loading conditions, we can design prosthetic joints that replicate natural biomechanics more accurately while minimizing failure risk. By doing so, we hope to enhance the performance, durability, and safety of hip replacement implants. With this foundation, let's delve deeper into our study objectives and findings.
Hello, Doctor. My name is Shana, and I'll be covering the literature review of the presentation. The objective of a literature review is to ensure the data has been compiled, and this can be compiled in many different ways. The ones that I have listed down here are systemic reviews, original research, surveys, case studies, and technology reviews. This is especially important so that we can get the data from all of these different types of evaluations and enhance the experience for future patients using the result of these data. The main objective of the literature review would be so that we can get the raw data and use it to enhance the experience for future patients of the total hip replacement. Any way that we can design it and make it better, and any input we get is highly valuable and important. So, this can help us. For example, combining patient centered insight with new technologies can improve outcome and quality of life.
My name is Fatih Natasha, and today I'll be presenting methodology. And so, first, let us look into the materials that are being used. So, a large variety of implant devices has been proven to improve the quality of life of many people who had such procedures done in their life. The primary material used for a variety of application in medicines are usually synthetically made, and the application can range anywhere from total replacement of heart tissues, repair, diagnostic, or corrective devices. So ideally, a bone implant such as hip implant should be exhibiting an identical response to loading similar to real bone. It must also be biocompatible with the existing tissue in order to avoid unwanted biological response of the patient's immune system towards the implanted device. And so, a typical hip implant is usually fabricated from titanium. Although there are other materials that can be used, we tend to choose titanium for several reasons. So let us look at the properties of the other materials. So typical polymeric materials alone tend to be too weak and appear to be unsuitable to meet the requirements of stress deformation responses in the total hip replacement components. Subsequently, a metal exits to be excellent by mechanical properties but shows poor biocompatibility as it causes stress shielding and also release of dangerous metal ions that will eventually lead to failure and need to be removed from the patient's body. And another material which is good in terms of biocompatibility is ceramics. However, it shows poor fracture toughness and exhibit itself to be brittle. The next part of methodology is the experimental setup, and there will be a few experiments that we will look into. First is the finite element analysis. So there are two parts of this experiment. Firstly, the laboratory testing will be carried out on a femur, including the compression, torsion, and also the Brinell hardness testing. A compression testing is done using strain gauge technique done on the hip implant itself, and afterwards, through the finite element analysis software, the software will be used in order to simulate all compression and torsion testing, assuming the same boundary and loading conditions, and subsequently, The computational results will be compared with the earlier experimental data in order to verify the experiments and models that are being used. This finite element analysis, which is verified by experimental testing and holding clinical relevance, were used in order to decide the best optimal hip stem design amongst different presented designs concepts. The second test is the mechanical testing. So mechanical testing test is performed on a servo-hydraulic test system. Approximately, each specimen which has been obtained will be attached to the machine actuator via a ball and socket joint. The testing protocol comprised of a quadratic and a cyclic loading part. Based on the load displacement curve, axial construct stiffness, failure load, and cycle to failure, which will be defined as parameters of interest for each specimen and considered for statistical evaluation. Axial stiffness was calculated from the gradient of the respective load displacement curve during the ram loading in the quasi-linear elastic region before the plastic construct deformation occurred, and failure load, cycles to failure, and type of failure were defined from the destructive cyclic test itself. The third and final experiment which will be conducted is the biomechanical analysis. So in this analysis, the specimens, or specifically embalmed human cadaveric femora from donors, which has been obtained, were paired and implanted with either an uncemented press-fit stem or an LSH stem, and then it will be tested biomechanically under progressively increasing cyclic axial loading until catastrophic failure. Next is the calculation. Before the calculations were done, there were a few assumptions that were made. Firstly is that the hip processes are totally new and all forces and loadings applied are exerted completely and precisely on the components of the hip processes. The components of the hip processes are in static equilibrium condition. There are no movement of the hip processes in the instantaneous position by external forces, so that the weight of the patient are exerted fully on the hip processes itself. And third, the patient is in an instantaneous position where he or she is standing on the ground and is not supported by any external support or forces at all. The fourth assumption is that the weight of the patient is exerted equally on both sides of the hips. The fifth assumption is that the calculations are accurate since the measurements are taken from GrabCAD website, which eliminates the possibilities of any human error or measuring apparatus error. The next assumptions that were made is that the weight of the patient was assumed to be 60 kg, and we also assumed the material of the hip prosthesis to be made from titanium alloy.
Result: free body diagram and force. Calculation confirmed proper load distribution across the prosthetic components, minimizing stress concentrations and ensuring stability under standard standing conditions. Torsion, bending, and axial forces. Torsional stress: the titanium prosthesis effectively restricts twisting force with minimal deformation. Bending stress: the prosthesis handles bending moment within safe limits during regular activities. Axial stress: compressive loads and well distributed, ensuring the prosthesis remains durable under pressure. Inertia calculations. The mass moment of inertia and area moment of inertia were calculated for the prosthesis. Results demonstrated optimal resistance to rotational and bending forces. confirming the prosthesis the structural integrity during dynamic and static activities. Stress and strain analysis. Stress distribution. FEA results shows even stress distribution across the prosthetic component, reducing the risk of localized wear or fatigue failure. Strain analysis. Deformation value and load were minimal, confirming the prosthesis capacity to mimic natural joint biomechanics without compromising. Experimental validation. Mechanical testing, including compression and cyclic loading, validated computational findings. The prosthesis demonstrated higher axial stiffness, excellent fatigue resistance, and maintained structural integrity after extensive cyclic loading, highlighting its long-term durability. Material performance. Composites. Material combine titanium, ceramic, and polymers. Achieved a balance between mechanical strength, biocompatibility, and fracture toughness. Titanium's higher shear modulus, 45 GPa, contributed to this suitability for TPR, while ceramic provided enhanced biocompatibility and wear resistance despite their brittleness.
Hello, good morning or good evening everyone. My name is Ahmed and today I will be doing the conclusion part for the static assignment for group 11. So in conclusion, our research underscores the critical role of statics and mechanics in optimizing the design and performance of total hip replacement by carefully analyzing the forces acting on the hip joint, selecting appropriate materials, and utilizing advanced computational tools like FEA. Engineers can create implants that more closely mimic the biomechanics of natural joints. Our findings demonstrate that by focusing on optimized load distribution, material selection that balances strength with biocompatibility, and ensuring implant stability, we can significantly reduce the risk of implant failure, such as loosening, wear, and material degradation. Furthermore, this research emphasizes the importance of a multidisciplinary approach, incorporating biomechanics, material science, and clinical data to drive innovation in THR design. By continuing to refine our understanding of the complex interaction between the implant, the surrounding tissues, and the patient's lifestyle, we can strive towards developing THRs that provide long-lasting, reliable, and pain-free solutions for individuals with hip joint disorders. Thank you everyone for listening and I hope you have a nice day. Thank you.